Lesson 10, Ultrasonic Testing. Introduction to Ultrasonic Testing. Ultrasonic testing, abbreviated UT, is an NDT method used primarily to perform volumetric inspections of components and to interrogate what is not visible on the surface of the part. The term ultrasonic refers to any sound where the frequency range is above the audible level of human beings, which occurs at above approximately 20,000 Hz. For nondestructive testing, most ultrasonic inspections occur above 1 MHz. By introducing the ultrasonic sound wave into a test object, the inspector evaluates the time the sound takes to get back to the transducer as an echo, as well as measures the amount of sound energy or amplitude of the returned signal. By analyzing the time and amplitude, the inspector can locate and identify various types of manufacturing or service-induced discontinuities, such as cracks, porosity, and inclusions. Ultrasonic testing originated from sonar, the technique of sending sound waves through water and observing the returning echoes to locate and characterize submerged objects. UT evolved in the 20th century with medical applications of ultrasound to find anomalies such as tumors and gallstones. Research and refinement of ultrasonic testing in industrial applications followed directly behind and continues this day with better technology to evaluate new materials. Advantages of ultrasonic testing. The detection of surface, near-surface, and subsurface discontinuities. Ultrasonic testing is one of really only two NDT methods that are considered fully volumetric, meaning that they can test the entire thickness of an object regardless of how thick it is. That's ultrasonic testing and radiographic testing. Ultrasonic testing is highly sensitive to discontinuities that are critical to structural integrity. It's highly portable. It's good for inspection of uniformly shaped parts. You obtain rapid inspection results. The approximate discontinuity size can be done with advanced systems. You can test through paint coatings if they're in good condition. You can inspect thick or long pieces up to 40 feet using pulse echo. You only need access to one side of the part if you are using pulse echo, but you are required to have access to both sides of the part if you're using a technique called through transmission. It works well on composite materials. Limitations of ultrasonic testing. Complex geometries can be difficult to inspect. Loose coatings or scale can impair effectiveness of the inspection. It requires a coupling to eliminate the air gap between the transducer and the material. Parts that have a propensity to attenuate, meaning they scatter or absorb sound, may not be able to be inspected. Interpretation can be difficult and requires a high level of experience. Training can be more extensive than many other NDT methods. And discontinuity orientation may create detection difficulties. Basic principles of sound. Understanding how sound energy is utilized to find discontinuities in materials requires general knowledge of the basic principles of sound. In the animal kingdom, sounds are used for navigation and hunting. Bats, for example, use echolocation to hunt. They send an ultrasonic sound wave which bounces off insects. These echoes reveal the location of the prey based on the time it takes for the sound energy to return back to the bat. The amplitude of that energy determines the size of the prey. In a similar sense, NDT technicians use ultrasonic testing to locate and characterize discontinuities using reflected sound energy in a material. To thoroughly understand the characteristics of sound, you must break down the process to the atomic structure. The transmission of sound is characterized by periodic vibrations, which are represented by a mechanical wave that propagates through a medium. The sound wave from a person talking travels through a medium, in this case the air, and enters the ear canal, where the mechanical wave vibrates the eardrum. The resulting vibrations are converted into electrical impulses which are sent to the brain. NDT uses electrical energy to excite an element mounted inside of a transducer to vibrate at a high frequency but with low energy. A low energy crystal is used to ensure no damage is caused to the part being inspected. The energy of the vibrating crystal causes the molecules in the medium, in this case the part being inspected, to also vibrate. The molecules are displaced from a resting state by the applied stress and move to a distance away from the resting state known as their maximum displacement. Then the molecules move back to their original resting place. This completes one half of one cycle of wave propagation. These cycles continue until the energy is removed. These continued cycles are what create the ultrasonic wave to be formed inside of the part. The ultrasonic wave consists of two parts as it propagates through the test specimen. The first part of the wave front is when the molecules are closely packed together, called the compression stage. The second part of the wave front is when the molecules are spread apart, known as the refraction stage. The molecules continue to compress and expand as long as energy is applied. A good way to visualize the compression and expansion of the molecules of the wavefront as it travels through a medium is to envision the contractions and expansion movements of a spring. The distance between two successful compressions or two successive refractions is one wavelength. Reflection. One of the properties of ultrasonic vibrations is their similarity to light energy. UT vibrations, like light, can be made to travel in distinct, well-defined beams. Additionally, they will reflect off of an interface at the same angle that they struck the interface. A good way to look at this is to visualize the game of billiards. If needing to bank a shot, that is, have it rebound off one wall of the table before hitting the pocket, it is generally known that the cue ball will bounce or reflect at the same angle at which it strikes the bumper. In ultrasonic terms, the angle of reflection equals the angle of incidence. Refraction. Another principle of sound is refraction. Refraction occurs when a sound wave is introduced into a test specimen at an angle not normal to the surface, and that wave bends or a portion of it refracts. This is another principle that is similar to light. If looking at a straw through a medium like water, it would appear as though the straw were bent. This refraction occurs because of the different refractive indexes of air and water. In ultrasonic terms, the sound bends because of the different acoustic velocities of the materials. This can be calculated using a formula known as Snell's law. Snell's law is the sine of the incident angle divided by the velocity of the first medium equals the sine of the refracted angle divided by the velocity in the second medium. Sound wave propagation modes. Ultrasonic sound waves have different modes of propagation. There are four basic wave propagation modes, which are based upon the way the particle motions are generated. They are 1. Longitudinal waves, which are also called compression waves or primary waves. 2. Shear waves, also called transverse waves. 3. Surface waves, which are also called Rayleigh waves. And 4. Plate waves, which are also called Lamb waves. Longitudinal waves. Longitudinal waves have a particle motion that occurs in the same direction as the wave propagation. They're the most common used wave mode in ultrasonic testing. Longitudinal waves occur when the sound is introduced into the part normal to the surface. In other words, the transducer is placed directly or indirectly perpendicular to the test surface. Some other specifics to longitudinal waves are, they have the highest velocity of all modes, meaning the speed the sound travels through the test piece. They have the longest wavelength of all modes. They have the lowest sensitivity of all modes. They are the only wave that can travel through all media, meaning solids, liquids, and gases. This sound wave propagation is similar to audible sound wave characteristics. Shear waves. Shear waves have a particle motion that occurs perpendicular to the wave propagation. Shear waves are traditionally used to inspect weld areas for manufacturing and service-induced discontinuities. Shear waves occur when the sound enters into the part at an angle and the sound wave refracts in the part, as we previously discussed. The transducer is housed on a wedge to introduce the sound into the part at a specific angle to cause the refracted angle needed for the inspection performed. Some other specifics to shear waves are, they have a velocity of approximately half the speed of longitudinal mode. They have a shorter wavelength than longitudinal mode. They are more sensitive than the longitudinal mode. They travel only through solids. Surface waves. Surface waves have a particle motion that is elliptical in shape and are confined to the surface of the part to a depth of approximately one wavelength, with an effective examination depth approximately half of one wavelength. They are most commonly used to inspect the surface of parts for in-service discontinuities. Like shear waves, they are introduced through a wedge at an angle to produce a refracted angle, which bends the sound all the way to the surface. Some other attributes of surface waves are, they have a velocity of approximately 90% the speed of the shear wave mode. They have a shorter wavelength than the shear wave mode. They are more sensitive than the shear wave mode. And sound waves can travel around smooth bends. Plate waves. Plate waves are similar to surface waves as they are constrained to the surface or near surface of the part being inspected. They are traditionally used to inspect very thin plates or bonded composite components. The plate wave can be generated by one transducer and carried through the thin material to the receiving transducer. This methodology is often called the pitch-catch technique. Plate waves are most commonly used to inspect for surface-in-surface discontinuities along plates, such as disc bonds or delaminations in bonded structures or over long distances in piping. Velocity, frequency, and wavelength. Ultrasonic testing sensitivity is based on the size of the wavelength used to interrogate the part. A wavelength is the distance from one point on a wave to the next corresponding point on the wave. It is represented by the lambda symbol. To make the distance of a wavelength smaller and in turn increase the sensitivity, the inspection frequency is adjusted. The higher the frequency, the smaller the wavelength, and the smaller the discontinuities that can be found. By increasing the sensitivity, penetration ability is decreased. To determine the size of the wavelength, the following formula is used. Wavelength equals velocity divided by frequency. The smallest discontinuity that can be found during ultrasonic testing is equal to approximately half the size of the wavelength of the sound wave. As the frequency is increased, the size of the discontinuities that can be detected decreases. So the objective is to use the highest frequency possible to increase detectability. Transducers. The creation of an ultrasonic wave traditionally requires a transducer made from piezoelectric material. These materials have the unique property of being able to take electrical energy, convert it into mechanical energy, and then take the returned mechanical energy and convert it back into electrical energy. This principle is similar to the mechanical energy created through the use of a tuning fork. As the fork is energized, it vibrates a mechanical wave at a specific frequency set by the length of the fork. In ultrasonic testing, the specific frequency is set by the thickness of the crystal. The thinner the element, the higher the frequency, while conversely, the thicker the element, the lower the frequency. In the early days of ultrasonic testing, transducer elements were made from elements such as quartz and other natural crystals. These transducers were not very efficient, so over the years transducers have evolved from natural crystals to piezoelectric ceramics and piezoelectric composites, which are much more efficient and easier to mass produce. The dead zone. As we just discussed, transducers convert electrical energy to mechanical energy and back again. This process takes time, and because there is an area immediately under the transducer where there's not enough time for the transducer to both send and receive the energy, this area, in which no inspections can be performed, is known as the dead zone. There are ways to remove the dead zone by using either a delay line or water path, which places the dead zone outside of the part and into those mediums. The near field. The area after the dead zone, where the timing of the sending and receiving of the signals is interrupted by the incoming and outgoing wave fronts. This area is known as the near field or Fresnel zone. The near field can be used for inspections, however the accuracy of the amplitude cannot be counted on for the discontinuity sizing. Therefore, inspections in the near field are not recommended. The size and length of the near field can be calculated using this equation. NF equals d squared divided by 4 times the wavelength. The far field. Following the near field is the far field. The far field is also known as the Fraunhofer zone and is the area where the sound energy starts to diverge or spread, and the amplitude of that energy starts to decay exponentially. The point where the near field and the far field meet is the area with the greatest sensitivity. After that point, the sound energy decays while the ultrasonic beam begins to spread. Types of transducers. Different types of transducers are used depending on the type of inspection. There are straight beam, angle beam, surface beam, and dual element transducers. Straight beam transducers. These transducers are primarily used for determining material thickness. They are designed for the transducer face to be in direct contact with the test object surface. These transducers are typically pulse echo transducers, where the same crystal both produces and receives the sound waves. Angle beam transducers. Angle beam transducers use a wedge to refract a sound beam into the part at an angle. This refracted angle can be set based on the wedge material and the angle that the wedge is cut at for the known velocity of the part material. They are not designed to be used without a wedge. They're used heavily in the inspection of welds. Surface beam transducers. Surface beam transducers have wedges that are cut at an angle such that it creates a surface wave. They are solely used to inspect the surface of parts. Dual element transducers. Dual element transducers come in various shapes and forms such as pitch and catch format. One element is set at a slight angle to produce a longitudinal wave into the part, and the second element, also set at a slight angle, catches the reflected sound wave. They can eliminate the effects of the dead zone and near field issues. They're used in near surface inspection and thickness measurements. Ultrasonic testing systems. There are three main types of conventional ultrasonic testing systems. All three systems have the ability to generate ultrasonic energy through the use of a pulsar, and although the systems have different capabilities, the main component that differentiates them is the way the data is displayed. The three types of displays are the A scan, B scan, and C scan. The A scan. A scans show data based on an XY grid pattern. The horizontal or x-axis is a representation of time, the time it takes for the sound energy to either travel to or through the part and return to the transducer, or the time it takes for the receiving transducer to receive the sent signal. The vertical or y-axis is a representative of the amount of energy that is received by either the sending transducer, as in the pulse echo technique, or the receiving transducer, as in through transmission. The more energy reflected back, the greater the amplitude in the y-axis. The B-scan. B-scans show data in a sliced plane profile view, where the timeline travels along the y-axis, and the position of the transducer is shown along the x-axis. The advantage of the B-scan is that the approximate dimensions of the discontinuities can be determined. The C-scan. C-scans show data from a top-down plane view, where the data are collected over a period of time with an encoder system. The encoded sections are layered to show a view that can be associated with its location. Ultrasonic testing techniques. There are three main ultrasonic testing techniques: direct contact, immersion, and air-coupled. Contact testing. As previously mentioned, contact testing can consist of straight beam testing, angle beam testing, or surface wave testing. In addition, contact testing can be performed using one or multiple transducers. The transducers are coupled to the part via a couplant, which is used to remove the air interface from the transducer to the part. Immersion testing. Immersion testing uses a water tank and waterproof transducers. It is used predominantly in manufacturing processes to perform non-contact inspections of large area metal and composite parts. Air-coupled testing. Air-coupled testing is becoming more prevalent in the inspection of composite structures when contact and immersion testing are not an option. Because of attenuation losses, low frequencies are used to perform air-coupled inspections. Ultrasonic testing modes. There are two main ultrasonic testing modes: pulse echo and through transmission. Pulse echo mode. The pulse echo mode uses one transducer to send and receive the ultrasonic energy within one housing. The size and location of the discontinuity is determined by the amplitude and location of the echo received back to the transducer. Through transmission mode. Unlike pulse echo, through transmission works by using two transducers that are aligned with the test part between the transducers. One transducer sends the signal, and the other transducer receives the signal. Discontinuities are identified by a partial or total loss of the received signal. Indication sizing is limited because the inability to identify in time when the loss occurred. Discontinuity detection. The types of discontinuities that can be detected with ultrasonics range from manufacturing discontinuities to in-service discontinuities. However, the key to determining whether a discontinuity can be detected is based off of some basic ultrasonic testing principles. Can the sound energy be introduced into the part? One of the biggest limitations to inspecting parts with ultrasonics is the limiting factor when trying to get the sound energy into the part. If the part has large grain boundaries, the sound energy can be attenuated to a point where UT cannot be performed. If the part has a rough surface finish, sound energy may be reflected off of the surface, again limiting the ability to perform inspections. Complex geometries can also be a limiting factor in being able to get sound waves to the area of interest. Is the change in acoustic impedance large enough to be detected? When the ultrasonic energy hits an air gap, whether it's the back surface of a part or a crack that is perpendicular to the sound energy, virtually all the energy is reflected back to the transducer because of the large differences in the acoustical impedance of the air and the parent material inspected. However, when the discontinuity and the parent material have similar acoustic impedances, the majority of the sound energy continues through the discontinuity, and those areas can be missed. An example of this is a tungsten inclusion in a carbon steel weld caused during the welding process. Is the discontinuity orientated in a manner that the sound beam can be interpreted and returned to the transducer? When performing ultrasonic testing, it is ideal to have the expected discontinuity orientated in a manner where the largest cross-section is perpendicular to the primary sound beam. As the discontinuity becomes more in line with the primary sound beam, the detectability of the discontinuity decreases. Sonic transmission factors. Limiting factors. Large grain boundaries. Sound energy can be attenuated to a point where ultrasonic testing cannot be performed. Rough surface finish. Sound energy may be reflected off of the surface. Complex geometries. Acoustic impedance factors. When ultrasonic energy hits an air gap, virtually all the energy is reflected back to the transducer because of the large differences in the acoustic impedances of the air and the parent material inspected. When a discontinuity and parent material have similar acoustic impedances, most of the sound energy continues through the discontinuity, and those areas can be missed. Discontinuity orientation factors. When performing UT, it's ideal to have the expected discontinuity orientated in a manner where the largest cross-section is perpendicular to the primary sound beam. As the discontinuity becomes more in line with the primary sound beam, detectability decreases. And that concludes this lesson.